All right. Yeah, so this is a little bit of a smaller topic than usual compared to some of the previous ones, but it's still important and still shows up on gift equals MA. So it's still important to know. Yeah, so just orbital mechanics, so Kepler's laws and some related facts. So let's just get started with the theory, and then we'll jump into the problems. So of course, I mean, so for most of these problems, what we're going to be assuming is that there's a sort of central mass m, which can be viewed as the sun, and then there's some sort of little mass m doing orbits around this this bigger mass. And you can sort of view the big M as like the sun and the little m as the Earth, and then it'll be this is sort of the usual setup. And as you all probably already know, that there's this notion of circular orbits, which is which is that if you have a small mass m orbiting around a larger mass, and we'll always assume that the larger mass is much bigger than the smaller mass. What this amounts to saying is that the larger mass can be assumed to stay fixed. In reality, they're both orbiting around their center of mass, but since the larger mass is much larger, we can assume the larger mass stays fixed. Anyways, but now if we have a circular orbit like here, then what happens is that you can sort of solve for the velocity that the speed that the circular orbit must happen at, and if you know the radius. So in particular, we know here that the gravitational force, as you learned last time, between them is gmm over r squared, and then this must equal the centripetal acceleration times the mass. This is just F equals ma. And then therefore we get that v is equal to root gm over r. So this is the sort of speed of circular orbit. But then, as you also probably know, that you can also have non-circular orbits, which is sort of what this picture is trying to illustrate. But let me try to draw a better picture. So yeah. So we can also have what's called elliptical orbits, and in general, any conic section. So that would also include hyperbolic orbits, but sort of the most important case is elliptical orbits. And basically, an ellipse is a geometrical object similar to a circle. But it's like a squished out circle, but it also has two foci, here and here. And then I'm not sure if I should go over the definition of an ellipse. I guess I'm just going to assume that everybody's familiar with how an ellipse works. And then the point is that the sun is going to be at one of the foci of this ellipse. And then the mass is going to be orbiting that. So this is actually what Kepler's first law says. Kepler's first law says that any orbit around the sun of a planet follows an ellipse with with the sun at one of the foci. All right. So any questions about that? About the orbit, just Kepler's first law in general? Just put them in the chat if you have any questions. You can send them either privately to me or just send them to everybody. Okay. No questions so far, so let's move on. Yeah, and then in the ellipse, one important quantity in the ellipse is called the semi-major axis. And sort of the semi-major axis is half this length. So this is 2a, and then the semi-major axis is a. For any arbitrary orbit equation, will we use the radius of curvature instead of capital R? And this, no. In fact, so you cannot use this formula that v equals root gm over r in a non-circular case. The first law only holds for capital M much greater than little m. That's a question. In general, we are working in that assumption where like the little mass, where the large mass is fixed and the little mass is orbiting in an ellipse around it. The general case is that they're both orbiting around their center of mass, and then the Kepler's first law will state that both are performing elliptical trajectories about the center of mass. Does that make sense? Actually, I think what I just said is not true. That's not true. Let me think. Yeah, they will not be performing elliptical trajectories about their center of mass, and I think you are right. Yeah, if capital M is much larger than M, then the focus is not at capital M, because both are moving now. Basically, what it'll be saying is that the vector between them, if you take their displacement vector, then that displacement vector will be traveling, will be having an elliptical trajectory. But yeah, this sort of only holds when capital M is much larger than little m. All right. Okay. Now, second law. The second law states that, so this is Kepler's first law. Kepler's second law states that the so-called equal area swept out at equal time. So Kepler's second law is actually telling us something about, so Kepler's first law told us about the geometric shape of the orbit. Kepler's second law tells us about how fast the planet travels that orbit. So what it states is that so you can sort of view this as a vector, right? Like I can sort of view this as the position. If I view the sun as the origin, and I can view the position of the little mass as a vector r, then as this mass is traveling in the ellipse, r sort of sweeps out a trajectory. And so like if you move from this mass, let's say from here to now here, then it swept out this much area. And Kepler's second law is saying that the sort of rate of area swept out is constant. Now, one very important thing to know about Kepler's second law, and this is something that they like to trick you with on FPeople's MA or ask you about, is that Kepler's second law is not specific to gravity anymore. Kepler's second law holds for any sort of central force. A central force is a force which is between two objects, and it always points towards the objects. It's an attractive or purely attractive or repulsive force, and its value only depends on the distance between them. That fact is not important, but yeah, but basically the important part is that they are either purely attractive or purely repulsive. So for example, just to tell you that not all forces are central. For example, if there's a magnetic interaction between two objects, then that's not a central force anymore. But you can learn that when you learn magnetism. But the point is that if there's a central force between two objects, then and one is much larger than the other, so like this configuration, Kepler's second law actually holds. And it still holds if the relationship is not inverse squared. It holds as long as the force is just purely attractive or repulsive at all times. And Kepler's second laws actually relate to a very important fact called, which is conservation of angular momentum. So I assume we've already covered angular momentum, but let me just quickly revise and just say what's, this is super important for orbital mechanics problems, which is that the angular momentum about the origin is conserved. And the angular momentum, so if the point is at if it's at here and it has a velocity, so the velocity is always tangent to the trajectory, then the angular momentum is mr cross v. So always points perpendicular to the page, but it sort of has value. The magnitude is mr v sine theta, where theta is the angle between them. And this is conserved, and this is conserved because if you think about the force between the two objects, it's pointing parallel to the vector r. So if you think about the torque, which is r cross f, it's the cross product of two parallel vectors. So the torque on this little mass m is always 0 about the origin. So therefore, the angular momentum is conserved. This is just a rotational fact. But this is very important in solving all orbital mechanics problems. And it turns out that Kepler's second law is a consequence of this. We're just going to derive it here really quick, just because it's an important derivation, which you might see many times. But yeah, these two facts are completely equivalent. And again, this fact, this proof that angular momentum was conserved only depended on the fact that the force was parallel to the r vector, so that the torque is 0. Okay, let's prove this. So the idea in this proof is the following. So let's say we have our mass here, And let's say we have our object at position vector r. Maybe I'll. Then let's say after some amount of time, the position vector changes to r plus dr. So it's changed by some amount, and this dr is the amount it's changed by. Right, and this is a sort of infinitesimal change in the position vector. And then let's say this happened over a time dt. All right. So first of all, what conservation of angular momentum tells us is that r. So if we let L be the total, L is total angular momentum, or L is the sort of let me write that again. L is the constant angular momentum value. Then this tells us that r across v is equal to L mr across v. And in this case, what this is saying is that mr cross dr dt is L, because the velocity is dr dt. And now it's you can sort of see that the area of this triangle is 1/2 r cross dr, just by geometry, because it's r times dr times the sine of the angle between them, 1/2 of that, so it's 1/2 r cross dr. And this implies that dA dt, I guess the absolute values are not needed there, because everything is pointing in the z direction. Yeah. So dA dt is 1/2. So if we use the product rule, then we get that it's 1/2 r cross dr dt plus 1/2 dr dt cross dr. Of course, this is 0 because this is two parallel vectors. So this is 0. And this is just 1/2 of by this equation right here. So this implies that the rate of change of the area is constant because the angular momentum is constant. So this is the derivation of Kepler's second law. And if you didn't get that, then you should look at the recording and watch it again and get the derivation. Also look at Morin, Morin's book, and you can find the derivation there as well. All right, so that's Kepler's second law. And a sort of important fact is conservation of angular momentum. That's sort of the fact that we'll be using a lot in problem solving. Okay, any questions about this derivation and about Kepler's second law before I move on? Why are you able to say the other side of the triangle is dr? That's a question being asked. Well, so what does dr even mean? Dr is the change in position vector. So if the position vector starts at, let me see how to get a, if the position vector starts here, that's not very good. Yeah, if the position vector starts here and ends here, then what's the difference in the position vectors? It's a difference of these two vectors, and the difference of those two vectors is exactly what I drew as dr. So dr is literally the difference in the final position vector minus the initial position vector. Yeah, it's just vector subtraction in this case. All right. Any other questions on Kepler's second law? Okay, does not appear to be any more questions. So let's finally mention third law, which is also important. And it states that So we're going to say a slightly more precise version than you've seen before. And it says that if you have a closed trajectory, so again, if you have an elliptical trajectory, essentially, and let's say you have an elliptical trajectory with semi-major axis A, then the period of the orbit, which is t, which is how long it takes to go all the way around, is this. In particular, what I want to draw your attention to, is that this sort of scales as t scales as a to the 3 halves, which is the important value. So the period scales as a to the power of 3 halves. That's the important thing. And then the sort of constant factor out here is also important. But what I want to say is that you can derive this constant factor by looking at circular orbits. Let's actually do that right now. So the sort of the form of Kepler's third law you've probably seen is this, that the period scales as semi-major axis to the 3 halves. Now, let me just show you how, if you forget the constant factor, you can derive it really quickly. The idea is that Kepler's third law implicitly is saying that the period only depends on the semi-major axis. And of course, there's many elliptical orbits of the same semi-major axis. In particular, we can consider just a circular orbit with radius a, which also is an elliptical orbit with semi-major axis a. And we can compute the period here. So again, if the speed is v, then we have mv squared by a is equal to gm m by a squared. So v is equal to root gm over a. And now the period is equal to 2 pi a over v, because 2 pi a is the amount of circumference it has to cover. V is the speed. And this is 2 pi a, which is exactly the formula we had before. So I just want to clarify, this is not a derivation of Kepler's third law, because Kepler's third law says that the same is true if you even have like a elliptical orbit with semi-major axis A. And here the speed is changing all the time. So you can't really just use this proof, but this proof that for circular orbits is important because it allows you to get the constant factor at any point in time, if you forgot it. It also gives a heuristic guess of why this a to the power 3 halves is sort of the right scaling factor. But Kepler's third law is actually saying something much stronger. Okay, also I got a question about general preparation. Why don't you ask that at the end, and I'll answer that at the end, because I don't want to distract from the focus right now. Cool. Right, so these are Kepler's 3 laws. Just first, again, it's just that they travel in elliptical, or in general, you can also have hyperbolic orbits. Second is conservation of angular momentum, but rephrased in terms of area. But again, the most important thing to remember here was that angular momentum is conserved. And third is this period as a function of semi-major axis. So any questions about any 3 of the laws? Okay. For hyperbola, what will be A? Okay, that's a good question. So I want to point out that you can't really use this formula anymore, because for a hyperbolic orbit, what a hyperbolic orbit looks like is it looks like this. So it sort of comes out from infinity and goes out. And in particular, this means there will be no period, because it'll never come back on itself. So this formula is no longer applicable. So that's just one thing that you should know. But in general, for a hyperbola, if you use, so I guess I'm gonna leave it at that. There is no value of A. But actually, I'm gonna come back to this when I talk about my next concept. Okay, so there's actually something like a Kepler's 4th law. It's not actually Kepler's 4th law because it wasn't discovered by Kepler, but it's just sort of an equally important law in in orbital motion, which is really, really useful. And it's sort of so obviously one other thing that we haven't covered so far is that energy is conserved as the planet is orbiting. So in particular, what that means is that 1/2 mv squared minus gm over r, where r is the distance to the ellipse. This is a conserved quantity. And again, L equals mRV sine theta, where theta is the angle between them. Is also conserved. So you have two conserved quantities, and you also have E. And the really important fact that you should just remember is that in an elliptical orbit, with semi-major axis A, the total energy is actually given by negative GMM over 2A. This is a very important fact. It allows you just to find the energy of the orbit as a function of little a. And again, you can see in the case of the circle, this is really easy to show, but the power of this comes when you use it on elliptical trajectories, where it's not at all obvious that this is the case. But this is just a fact that you should remember. All right. And sort of here now, this also holds for hyperbolic orbits. And I want to draw your attention to energy in orbits, which is another important topic. Energy less than 0 means that the orbit is bound, which means that it's elliptical or circular. And again, as you see, this energy value is negative, and in particular, if A is positive, and this is negative, as expected. So elliptical orbits give bound trajectories. And if E is greater than 0, then this orbit is unbound. And that means that for hyperbolic orbits, A should actually be a negative value. So if you sort of want to have effective A, you should take it to be negative, if that makes sense. But it doesn't have, my understanding is that there's not a very clear geometric interpretation of what you can draw it, that you can draw just onto here. Because like, yeah, it's not an ellipse, and I don't think you can very clearly just say what is a little a. All right. But yeah, this is sort of the E less than 0, E greater than 0 is bound and unbound. And then sort of the boundary case, which is E equals 0, corresponds to a parabola, which is sort of the exact turning point between an ellipse and a hyperbola. So sort of if you have an ellipse and you keep making it like larger and larger, then eventually it'll look like a parabola that just extends like this. And then if you make the energy even larger, then it'll become like a sort of hyperbola. All right. And then E equals 0 corresponds to the parabola. And this is related to the concept of escape velocity, where to find the escape velocity, which is the minimum velocity you need to escape, which is minimum velocity needed to be unbound, you want to set E greater or equal to 0. And that's how you can solve for the escape velocity in any case. All right. Any questions about its energy and the formula for energy and bound and unbound orbits? Very important concepts. Okay. Appears to be no questions on energy, formula for energy, and bound and unbound orbits. So if that's the case, we're going to get started with problems. Let's start with 2013, number 13, which is the first one. Can you explain what you mean by bound and unbound orbits? A bound orbit is just an orbit which will eventually come back to itself, and it stays within the sun. So, for example, planet trajectories are bound. Unbound orbit means that it'll never sort of loop back on itself. And in particular, many comets trajectories are, I believe, are hyperbolic. Don't quote me on this, but sort of some of these astronomical objects, obviously the ones that we know and love are bound orbits because we keep seeing them over and over again. But there are sort of other objects which only pass by the sun once, essentially, and they pass by in hyperbolic orbits. That is the notion of bound and unbound. All right. So let's start with F equals MA 2013, number 13. Just the first problem in the handout. And again, please open the handout from the email because we're going to be referring to that. Okay, so number 1 says that there's a ring outside Saturn. And in order to distinguish if the ring is actually part of Saturn or instead part of the satellites of Saturn, you want to find sort of the velocity as a function of radius. Radius was the distance to the center of Saturn. So what is the relation if it's part of Saturn, and what is the relation if it's part of the satellites of Saturn? So part of Saturn versus part of satellites of Saturn means that if it's part of Saturn, it means that there's sort of a pull connecting the ring and Saturn, and it travels along with the surface of Saturn. Part of the satellites of Saturn means it's traveling in a circular orbit just due to gravity. So how can you determine that just by if you're given the v as a function of radius of Saturn? Maybe I'll just give 30 seconds for everybody to think about this, and then we'll go over what it is. Okay, this is a pretty easy question, and part of Saturn means that v of r is proportional to r, so it's equal to kr for some constant k. Reason for this is that if you're attached with a pole to Saturn, then you're sort of the v is actually exactly equal to omega r, so the constant is omega, where omega is the angular velocity of rotation of Saturn. And as you move farther and farther out, if you're attached by a pole to Saturn, then you're going to be moving with that same angular velocity. So if v is proportional to r, then you can safely say that that object is attached to Saturn. And satellites, as we saw before, we have this formula for the circular orbit speed from right here. So v of r is, so basically so here v of r is proportional to 1 over root r. So if it's proportional to 1 over root r, then you can say it's part of the satellites. All right. Any questions about this problem? I think the hardest part about this is sort of distinguish what it means to be part of Saturn versus part of satellites of Saturn. All right. Let's move on to the next one. So this one is on the last page of the document. Okay, this one is not really strictly speaking orbital mechanics. In fact, there's no gravity necessarily or anything. But what is there is that there's this is a conservation problem, and sort of the same ideas used to solve this problem are very important in analyzing orbits. So in that sense, it's a very similar important problem. So we're given two masses, and you're given their starting trajectories, and they evolve through internal forces only. And these internal forces sort of you can implicitly assume that they are central forces, that they are pointing to each other. Let me think if that's necessary. Actually, that's not even necessary. But anyways, so you have these two objects and they interact only through internal forces, and what is the possible outcomes for how they end up? Okay. So let's try to solve this. So maybe why don't people just put in the chat what are some conserved quantities they can use to eliminate choices? So why don't you just put one thing you can eliminate by looking at the conserved quantity? Or you can even unmute and say it if you know how to eliminate at least one of these choices. If CM is not conserved. Okay, great. Ben just said that you can eliminate A because the center of mass is not conserved. Very good. So center of mass is the first conserved quantity. So because of some external forces, the center of mass must stay fixed. And the center of mass is sort of at this point 1, 0 in the original picture. And for A, it's not at the center of mass. The rest of them work, but this allows us to eliminate A. So cool. Center of mass got rid of A. So actually, why don't people mention something else, and then we'll hopefully through the chat we can get rid of all the choices until we're left with just one. Okay, somebody says E can eliminate E since they can't grow farther apart because gravity is attractive. Well, not necessarily. The problem, first of all, the thing here is not gravity. It could be repulsive as well. It could be electric repulsive. So we don't know that. And second of all, there's nothing really stopping them from going farther apart because, well, I mean, the idea is that technically if the speed decreased, that they could go farther apart. Because if the energy goes from kinetic to potential. Okay, somebody said moment of inertia. Moment of inertia is not a conserved quantity. Moment of inertia is more just like mass. Can we eliminate? Yeah. Okay. So two people have mentioned we can eliminate B because energy is not conserved. That is correct. That's what I'm going to talk about next. Yeah. So the energy between these two objects. So first of all, we don't know it's gravitational. So we cannot even say that the energy is negative GMM over R or anything like that. But what we can say is that if they're the same distance apart from each other. Let me think. Is this? Hold on. Give me one sec. Yeah. Okay. So actually, energy we cannot. This is actually a good point. We cannot use energy. I just realized that. The reason is that we don't really know. We don't really know the form of the potential energy between these two objects. Like we said, we don't know it's gravitational, and technically, we don't even know. Theoretically, if it just depends on the distance between them. So we can't. I don't think we can just use energy to eliminate B. But we can eliminate B using another very simple thing. Somebody mentioned that we can eliminate B because of conservation of momentum. So it's actually much easier to eliminate B. And momentum conservation doesn't depend on the form of the energy or anything. So momentum conservation, the momentum is originally 0. And then in B, it's not 0. Okay, great. So you got rid of B. And that does not get rid of any other ones because all of the other ones have 0 momentum. Eliminate C and D because angular momentum. Okay. Let me think about that. Yeah. Yeah, exactly. So the final conserved quantity we'll use is angular momentum. And we'll use angular momentum about the center of mass. And then in the first case, it's just sort of like 1 meter per second times 1 meter plus 1 meter per second times 1 meter. And in C, it's sort of 1/√2 meters per second times 1 meter, because there's a 45-degree angle. So you have a factor of that, of sine 45 degrees. So again, not equal to the original angular momentum. So C is eliminated, and D, you sort of have a angular momentum of 2 meters times 1 meter per second. So again, not matching up. And this only leaves E. And as if you can easily check that the CM momentum and angular momentum in E are the same as they are as it is in the original case. Any questions about this one? All right, could you go over how angular momentum is conserved in E? Yeah. Also, one implicit fact I'm using about angular momentum here is that sort of an alternative way to calculate angular momentum. Obviously, r cross v, so rv sine theta, is the standard way. But let's say you have v here and you have r here. Oftentimes, instead of computing the angle between them and doing rv sine theta, you can sort of do all the geometry by saying r you can sort of say r projection right here. If you say this is the projected value of r, then the angular momentum is just rp times v. Because if you think about it, this is the angle here, then sine sort of r times sine theta is equal to rp, if that makes sense. Does that make sense? All right. Cool. So let's cover F equals MA 2014, problem 22 now. All right. This one's a bit a long one, so why doesn't everybody just take some time to read it, and then we'll go over the solution. And also take some time to think about it. Okay. So this is actually a problem where we cannot use the mass fixed approximation. The mass fixed approximation, because what's important here is sort of the fact that they're orbiting around the center of mass. So we're gonna have to actually use that. And in the problem it says they orbit around their center of mass. All right. So yeah, let's say there's enough masses here, cm, and they both are orbiting around it. Okay. So we want to find sort of the gravitational force as a function of the masses. The angular momentum is a function of masses, and the period as a function of the masses. And then we'll see if we change the masses a little bit and keep the distance between them fixed, how do these quantities change? So obviously, gravitational force between them is gm m over r squared. And if we change the masses, so sort of m goes to m minus delta m, then this product will change, and therefore the gravitational force will change. So that eliminates A. Okay. So that actually eliminates A and B. Because it, oh, oops, it doesn't necessarily eliminate A. My bad. Let's just think about that real quick. So it eliminates B because the gravitational force doesn't remain constant, but we're trying to find A. So the gravitational force is originally some constant times little m times m, and then it goes to this value, which we can write as sort of and sort of imagining little delta m is much smaller than all of them. We can see it's the original quantity minus something times delta m, because capital M is. So therefore, the gravitational force actually decreases, so that eliminates choice A. Okay. So now we have to find the angular momentum between these two objects, sort of the total angular momentum about the center of mass. Let's do this right now. So now we'll need to use the fact that that because this is the center of mass, this distance is these distances are just chosen that they sum to r, and that they're and that's just that the center of mass is the same. All right. Now, what we can say is that, let's say the velocity here is v1, and the velocity here is v2. All right. Then what we can say is that the total momentum of this system is 0 because the center of mass is not moving. So we can say that m v1 is equal to little m v2. Exactly. Because the problem says that the distance between them stays the same. The problem says that the distance between them stays the same, so you don't have to take into account that. Yeah. So we have this equation for the velocities, and then we also have the F equals ma equation that gmm over r squared is equal to m v1 squared by. All right. And this implies that v1 squared, m v1 squared is equal to so this implies that v1, have I made a mistake here? No, I'm fine. I think I've made a mistake here. Does somebody want to help me figure that out. No, I've not made a mistake. Yeah, this is fine. And then V2 is equal to root by similar logic. Okay, these are the values of the velocities. And then this implies that the total angular momentum is equal to plus little m because this capital M distance V1 and this just becomes Rm times V1 plus V2. So it just becomes Rmm times yeah. So the total angular momentum is then which is equal to m root g r over m plus m. Yeah, this long calculation tells us that this is the formula for angular momentum, total angular momentum. Cool. Great. So yeah, now let's see what happens if we again now do m to m plus delta m and m. So obviously D is eliminated. So again, we have A, B, C, D, E because the angular momentum is not going to stay constant. But now the question is, does it increase potentially? So the relevant quantity is this. And this now goes to m plus delta m. And this stays the same because the sum stays the same. And as we saw, this quantity actually goes down. So therefore, this entire quantity goes down. So this also eliminates C. Cool. All right. So finally, we have to find the period. So, okay, obviously now we already know the answer is E, but I'm just going to calculate it to show you how you calculate the period. So we already have the formulas for V1 and V2. So I can just say it's the period, if I just do it right here, is just 2 pi over V1. So let me just do that calculation over here. So it's 2 pi. This is the radius of orbit of the big mass. This is the speed of orbit of the big mass. And if we divide by V1, we get times R over GM squared. Which ends up becoming 2 pi root R cubed over GM plus M. So wonderful. As we see, this only depends on the sum of the masses, and that stays the same. So therefore, the answer to the problem is E. All right. Any questions about this problem? Any questions about any of these? Where we can find the recordings for previous lessons. Each instructor sent it individually in an email. I don't think there's a shared repository. For any previous recording that you don't have the email for that one, you should just email the instructor for that week and just ask them for the recording. But yeah, I'm not aware of any place where you can find all of them in one location, unfortunately. Okay. So any questions about this solution? Okay, great. Let's move on to the next one. So actually, I think let's do problem 5 first because problem 4 is a bit harder. Then we'll go back to problem 4. Then we'll do 6 and 7. So we'll start with problem 5. So it's F equals MA, 2017, number 5. All right. This is going to be a sort of the first hardcore elliptical problem where we're going to have to do all the angular momentum and Kepler's law things. So get ready. All right. Cool. So yeah, it feels I made 27, not 5, my bad. 25. Okay. So they've told us this is 0.5a, and then therefore, since the semi-major axis A, this is 1.5a. We're given the velocity here, v2, and we're asked if we take sort of this point exactly here, what is v1? Okay. So again, this v1 is going to be parallel to the ellipse here, so it's not going to be exactly horizontal. It's going to be a little bit pointed down. Okay. Okay. So let's solve this equation. Let's solve this problem. So what fact should we try to use here to solve this problem? Okay, somebody mentions vis viva. Yeah. So in fact, what we're going to use energy conservation. Angular momentum is conserved. That's a good fact. We'll see if that ends up being used. So this viva is actually just equivalent to E equals negative GMM over 2A. Completely equivalent. So we're instead going to just use E equals negative GMM over 2A. So we're going to be looking at energy conservation. And if we need to, we'll look at angular momentum conservation. So like the fact that I mentioned before that's super important here is that the total energy of the orbit is negative GMM over 2A. All right. So what does this tell us? This tells us that if we look at it for V2 is equal to negative GMM over 0.5A plus 1/2. This is the energy conservation for V2. Now for V1, it's a little bit more complicated since we need to find this length right here. But this is not too hard with some geometry, and let's just do it real quick. So if we draw the other focus here, what we know is that by the sort of definition of focus, the sort of two bolded lines, they must sum to 2A. That's sort of another alternative definition of ellipse. If you have the two foci, then those distances sum to 2A. And so if we say this is 0.5A, then I can sort of write this is A. Then I know that if this distance is let's say x, y is a better term. This is root A squared plus y squared. So I know that y plus root A squared plus y squared is equal to 2A. So this implies that root A squared plus y squared is equal to 2A minus y. And if I square now, I get that y squared plus A squared is equal to y squared minus 4ay plus 4a squared. So 4ay is 3a squared, so y is 3/4 a. All right. And what that implies here is that negative GMM over 2a for 0.75a. And this is actually now enough to solve for V2 and V1 in terms of A, and this will solve the problem. So let's just actually just do out the calculation. So 1/2 mv2 squared is equal to GMM over A times 2 minus 1/2. So it's equal to 3/2 GMMA. Four thirds minus 1/2. So that's equal to 5/6. So V2 squared over V1 squared is equal to what is it? 3/2 over 5/6. So V2 is 3 over root 5 times V1. All right. So now somebody mentioned about angular momentum, and this is actually a good point. But unfortunately, the hard part here is that you have to find this angle theta here. Then you can say that again, that y times v1 times sine theta is equal to v2 times 0.5a. And finding this angle theta is actually not really that easy. But just because let me outline how, if you want to use this approach, how you would do it. You'd have to use the fact that if you have a tangent to an ellipse, then these two angles are equal. This is just a geometric fact about tangents to ellipses, that the angles to the foci are equal. Then you can compute this angle because we know all the dimensions of this right triangle. And then you can, using that, you can compute theta and you can compute its sine. So it'll be a lot of trigonometry going to be involved here. But then you can eventually say v1 y sine theta is equal to v2 times 0.5a. Conservation of angular momentum. But the hard part is you have to compute that angle. So that's why the straight angular momentum approach is a bit trickier. And this sort of energy approach with this formula is the faster way to do it. Okay, any questions about this approach? No questions? All right. So again, the important factor was that E is negative GMM over 2A. Otherwise, we couldn't get a handle on these values. This is just a very, very important fact. Okay. Okay, looks like there's no questions. So let's move on to problem 4. Okay, so I'm not really going to draw a picture for this one because I think you should just use the picture that's given. So which of the following rankings is correct? This is a much harder problem in my opinion, and let's go over it. Because there's now inequalities and sort of the dimensions of the orbit are not specified to us, and rather we're just given some bounds on the dimensions of the orbit. That's why it's a bit harder in my opinion. Yeah. All right. Okay. So first of all, we can eliminate A and B pretty easily. Does anybody see how to do that? Kepler's second law? Sure. Basically, conservation of angular momentum. And conservation of angular momentum says that VA should be a lot bigger than VB. Because VA times the distance to the sun equals VB times the distance to the sun. And the distance to the sun at A is much, much smaller. So VA should be greater than VB, and this eliminates A and B. All right. This is just conservation of angular momentum. Of L. Okay. Now, in order to yeah. Okay, so any ideas on how to eliminate any of the other ones? D, because VA must be greater than VC. So how do you know VA is bigger than VC? So that's a good idea. We claim VA is greater than VC. But how do you know? Yeah, but so you're saying perihelion versus circular orbit. That's correct, but still, how do you know? For recording, you should email the just because RC is greater than RA doesn't imply that VA greater than VC. I think it requires more work because they're different orbits, right? So it's not just the same situation. Somebody's asking, can we eliminate C from VA greater than VB? No. C is saying that 10 VB is greater than VA. So it's still possible that 10 VB is greater than VA. Right? It's just not possible that that VB is greater than VA. If you multiply by 10, it could be bigger. VC greater than VB. No, it doesn't. It does not. So okay, so people are having a little bit of misconception. It's good to clear this up. VC greater than VB does not eliminate C. First of all, we don't even know this, but let's say we did know this. It doesn't eliminate C because C is saying that 10 VB is greater than VC. So for example, we have 1 greater than 1/2, but 10 times 1/2 is greater than 1. Somebody says, can't we use Kepler's laws? Sure. I mean, I don't think in this case we can use Kepler's law. We have to use something around energy or angular momentum conservation. So, yeah. Okay, I guess I think the only way to do this at this point is to actually calculate sort of what VA and VB would be. So the way I'll set this up is the following. What I'll say is that you have the sun here. Momentum B max case, what do you mean? Okay, Ben actually brings up a good point. So yeah, okay, before I talk about that, let me just set this up. So the way I'm going to set this up is that this is R times alpha, and this is R times beta, and the problem gives us that 1/2. Oops, my bad. 1/3 less than alpha less than 1/2, and 2 less than beta less than 3. Okay, right. So Ben is giving an argument for why VA is bigger than VC. So we already know that VC is equal to root GM over R. Right? This is just the circular orbit velocity. Now VA, yeah. So let's say VA. So I actually claim that VA is bigger than root GM over R alpha. The reason for this is imagine you had a mass right here, little mass, and you were to throw it and you were to try to make it in a circular orbit. So oh, does this argument not work? Yeah, I don't think this argument works. Let me think. No, yeah, it works. So if you were to throw it with a small velocity, then what you would get is if you were to throw it with a very small velocity, then you would get that the orbit looks something like this. If you throw it with a larger velocity, you'd get like this eventually until you get circular orbits. Sort of the scale of this picture is wrong, I guess. And therefore, you'd have to keep increasing your velocity until you finally get to this large elliptical orbit. And this is because this is much closer to escape velocity than it is to circular orbit velocity. So therefore, VA is actually greater than root GM over R alpha, just automatically then greater than equal to root GM over R. So this proves that VA is bigger than VC. So does anybody have a question about this argument due to Ben? That VA bigger than VC? The idea is that if I have a sun mass here and I have a little mass here, if I shoot it off with a very small velocity, then it'll just basically fall in and fall back out like that. And if I start shooting it with larger and larger velocities, I'll be getting until I finally get to circular orbit. Very shaky hand. And then if I shoot it with even larger velocity, then I get larger elliptical orbits So therefore, VA is greater than root GM over R alpha, which is greater than root GM over R. Okay, so this eliminates D. But I think to eliminate E, we still need to do some calculation. So we have to calculate VA and VC in terms of alpha and beta. This proves, okay, so somebody gave an argument to prove that C works, and I guess that is let me just think about that. Yeah, okay, that's actually a very good point. Let's talk about that. So for C, the claim, so we know that VA times R alpha is equal to VB times R beta. Oh, sorry, I guess VC times R beta. Oops, I messed this up. This should be VB. So VB over VA is equal to alpha over beta. And this is greater than or equal to what 1/3 over 3, which is 1/9. So VB is greater than 1/9 VA. So 9 VB is greater than VA. So certainly 10 VB is greater than VA. So this proves that 10 VB is greater than VA, as it is in C. And we already showed that VA is greater than VC. So this proves that that C works. So C must be correct. But let's also so I guess for sake of time, I'm not going to show exactly why E fails. But my thing is that my point is that you can use again similar laws to calculate VA and VB explicitly in terms of alpha and beta. And once you calculate them explicitly in terms of alpha and beta, you can and you can compare them to VC then and get you can just prove that E is wrong. All right. Any questions about this? So yeah, so this is a nice argument due to Rachel that this works. So any questions about this problem? No questions? All right. So if that's the case, let's move on. And we only have about 5 or 10 more minutes. So I'm just going to cover problem 7 because I think problem 7, it's a classical problem. It's very nice. It's a very nice trick. It's also a bit hard, but I just want to cover it because the trick in problem 7 is really, really nice. And it might show up in some harder Olympiad problems, but definitely not at the F equals MA level. But we'll just present, I'll just show it anyways. So problem 7. So the question is, you have the Earth, radius R, and you you drop a little ball at double that radius, and the question is, how long does it take to fall to the Earth? So you can no longer just use basic kinematic, like 1/2 gt squared, those types of formulas. You can't use those anymore because the gravitational force is varying over a function of distance non-trivially because you're all the way capital R out. So that now this sort of becomes a gravitational question, like gravitational force question. So any ideas on how to do this question? Just maybe just in the chat, just put some ideas and then we'll go over the actual method. G is a function of time. Yes. Yeah. So Ethan. Yeah, Ethan brings up a way to do this problem, which is that if let's say I call this position X, right? Then just Newton's second law tells me that mx double dot is equal to negative gmm over x squared. Right. So this is some differential equation that you could try to solve. but this is not necessarily very easy to solve. So if you write this down, you might get stuck. Now, the way to make the calculus batch approach work is to use energy conservation instead. So energy conservation tells us that mx dot squared, I guess, minus is equal to negative gmm over 2r in this case, where x of 0 is 2r. And now you essentially have x dot as a function of x. So you can say that dx over fx is dt by rearranging. And then if you integrate both sides, then you can get a relation between x and t. So this is a calculus way to approach the problem. But this is kind of bad. If you sort of look at the steps here, you'd have to do some sort of unpleasant integrals. It's not that bad. You can easily work it out if you have like 20 minutes. But there's a nice geometrical approach. And like Ahmed is saying, you can use Kepler's law, having a small semi-minor axis. Exactly. So again, let's for now ignore the surface of the Earth and just imagine that the Earth is just a point mass at the center. Then this orbit essentially looks like an elliptical orbit like this. And we can approximate it like that, as so. So in a very thin elliptical orbit, the focus is basically all the way at the left. Then in this case, the we know from Kepler's third law that the entire period is equal to root 4 pi squared over gm times a cubed. And here a, since this distance is 2r, a is r. This is the entire period. But this is not actually what we want. What we want is we just want the amount of time it takes for this mass to reach exactly halfway. So it's some fraction of the period. Now you might say this is just 1/4 of the period because it's just 1/4 of the arc length. But that's not correct. What ends up happening is that since it's moving faster as you're closer to the sun because of conservation of angular momentum, it traverses this arc length slower than it traverses this next arc length. So it's actually not 1/2. It's something more complicated. So what are we going to use to find the amount of time it takes to just go this 1/4 arc length as a fraction of the total period? How do you do that? Yeah, Kepler's second law, exactly. So let's draw this out. So you have the focus here. And you essentially want to find this area. Right? Now, since you have a very thin ellipse, you can essentially approximate this focus as being right at the edge. So what you can say then is that if we let this be B and we let this be A, we essentially have a triangle of area 1/2. Oh, my bad. Give me a sec. Yeah. So what you can say is that since this focus is all the way at the left, you can sort of approximate this as like this is not exactly the same, but since the focus is all the way at the left, you can approximate it as finding this area, this shaded area right here, since the focus is all the way at the left. Then if I draw this axis, this is A, this is B. What we get is that this this area on the left is pi AB over 4, because the area of ellipse is pi AB. And this triangle area right here is 1/2 AB. So the overall area is AB times 1/2 plus pi over 4. And the total area is pi AB. So the fraction is 1/2 plus pi over 4 over pi. So it's actually 1/4 plus 1 over 2 pi. If that makes sense. So it's a little bit more than a fourth. It's a little bit more than a quarter. So then therefore the amount of time it takes is 1/4 plus 1 over 2 pi times this is the amount of time. And this is the same result you would get if you were to do some integration. But this is a cleaner way to get the same result. Yeah, so somebody mentioned A equals VD, VDX, and replace, and so on. That's actually equivalent to this energy approach that you would do like this. So you would get the same exact calculation there. And yeah, you can certainly bash it out, and nothing's stopping you. It'll just take a bit of time, but it will work. Okay. I think that's all for today in terms of the problems. So you can try the problems we skip prompt 6. You can try that on your own. It's also a bit harder than usual, and you can do the 2 USFO problems I'd mentioned in practice for orbital mechanics. Okay, and yeah, somebody had a question about preparation beforehand. So by the way, you all are free to leave. I'm gonna stop the recording, and maybe I'll just stay here for 1 or 2 minutes to answer some questions, and then